Hello and welcome to this lecture titled Analysis of Algorithms. So today we'll be going into the details of the procedure how to analyze your algorithms. Now we have I have given you a little idea about how to analyze algorithms or why do we need to analyze algorithms. But today, before proceeding into the details of the analysis of algorithm, I would like to brush up or bring up two important points that are there because of which we do the analysis of algorithms. The first one is we should be able to compare two algorithms. So, what do I mean to say when I say we should be able to compare two algorithms? Means I should be able to have a quantitative judgment. Means which algorithm is better? Is algorithm A better or algorithm B better? Okay. The second reason why we do the analysis of algorithm is that sometimes there are some efficiency constraints that are put up by by the maybe the environment or maybe the person who is asking you to write the algorithms or by the machine itself. So at that times, if you want to implement those certain efficiency constraints, what you do, we do the analysis of your algorithms. Fine. Now, before proceeding any further into the analysis of algorithm, first we need to make clear what type of machine we are using. Okay, we have to see what are our assumptions about the kind of machine that we are using. Fine. So although formal model of machines exists, like we are having Turing machine or we are having random access machine, but for our study we will be using the conventional machine. Okay, so we won't be actually using, we will be rather considering a conventional machine. So what does a conventional machine means here? So here conventional machine has three things that we have to keep in mind. The first one is that when our algorithm is converted into a program and it executes on that machine, it is executed one instruction at a time. Okay. So the second thing that we have to consider in our conventional machine is that the major cost of our algorithm depends upon the number of operations that are being performed in our algorithm. Okay. And finally, the third one is that we are having a random access memory, means that we can access any memory location. By memory location, I mean a variable in a fixed amount of time. Fine. Now, these are the three things that our conventional machine has. But when I have mentioned these 3 points, a thought might have popped into your head is that right now we are having parallel architectures where more than one instruction is executed at a time. So what will happen then? Okay. So the another thing is that that the cost of hardware is drastically coming down. So a point might come in future where the cost of actually transferring data in your machine is more than the when you perform that operation. Okay. So these two things contradict our two assumptions of the conventional machine, that is the one instruction is executed at a time, and the second one is that the major cost of your algorithm is the number of operations it performs. So obviously, if we consider these two things, then we need to have a new model of computation. But for now, for our study, we will be considering a conventional machine where one instruction is executed at a time. Second, the major cost of your algorithm is the number of operations that you perform, and the third one is simply you have random access memory, means you can access any memory location in a fixed amount of time. Fine. Now, when we have to analyze your algorithm, we are having two tasks at our hand. So the first task is that we have to identify the operations and the costs associated with them. So the first one is operations and related cost. So if we think about the types of operations that can be there in our algorithm, the first one that comes to your mind is the arithmetic. So what are the arithmetic operations on your integers? The arithmetic operations can be plus, minus, into, divide, mod. So these are the basic arithmetic operations that you can apply on your integers, so that what will happen, it will take some time. Okay. The second thing that the type of operation that we can have in our algorithm is same, your arithmetic operations, but on floating numbers. Now the floating point arithmetic is a little bit different than your integral arithmetic. That's why I have shown it separately. Okay, so here also we have to consider these operations. Fine. The third one is your comparison. So comparison means comparison operations. So comparison operation simply means where you have to see if A is greater than B, or it can be an integer number, it can be a character, it doesn't depend on that. So this is simply your comparison operation. The fourth one is your assignment operation. So your assignment operation is A equal to B. What will happen? The contents of B will be assigned or stored in your variable A. Fine. The last type of operation that we can have is that we call it function or procedure. You know that whenever there is a function or procedure call, what happens? A context switch happens. So it will take some amount of time. So these are the operations that we have identified that can be there in our algorithm. And now we have to see how much time it will take. Okay, so the cost here is actually your time, your CPU time. So we will assume that they all are bounded by a constant time. Means whenever these operations happen, they will always happen in a constant time. If you are A plus B, it will always take same time. Means if you are adding two integers or multiplying two integers, it will always take same time on your conventional machine. And that means it is bounded by a constant. The only exception here is that if there is some complex operation which involves a combination of these operations, okay, at that time it won't be bounded by a constant time. For example, we are comparing two strings, then you have to individually compare your characters. So, and the length of strings can vary. So at that time it won't be bounded by a constant. But here, if we consider these basic operations and we look at their relative costs, we can see that they are bounded by a constant, means they are fixed. This is the first task. The second task is that what you have to do is that you have to think in terms of the data or the input to your algorithm. You have to think in such a manner that you have to create an exhaustive data set which will try each and every permutation and combination of your algorithm. Okay, so that is the second task. That's the second way how you can analyze your algorithm. You will actually think of the whole, your data set, the all types of inputs that your algorithm can take. You can give those inputs to your algorithm and you will see how it will perform. So just having said that, you can understand that how much complicated that can be, and that will really require some skills that you should possess, that you should have a total mastery over your algorithm, and you should know that what type of data it will take, and it has to be exhaustive, because unless it's not exhaustive, you won't be able to see how it is performing. Means if you are searching for a value in your array, you have to take the element at the first, element in the middle, or element at the end, or even if the element is not present. So if you miss any of these cases, you might look for the element at the beginning and you might think that your searching algorithm is working fine. But you have to think of a scenario. So this is a simple example. I'm telling you that you have to look for a value in an array. So at that time you will say, okay, it's fine, we can have an exhaustive data set. But all algorithms are not so simple, okay? There are some algorithms which are pretty complex, and at that time it will be difficult to design an exhaustive data set, okay? So now we will see the types of analysis. We are having two types of analysis, and we will have a look at them. If we look at the type of testing, we are having two types. If we look at the analysis, how we analyze your algorithm, we are having two types basically. One is your prior analysis and the second one is your posterior testing. You have already seen what they mean, but we have not given a formal definition to them. Now we will see a formal definition of these two. What do we mean by prior analysis is that whenever we identify some parameters and then we define a function based on those parameters that will give you the bounds on your algorithm, we say at that time that is your prior analysis, okay? So what we can take a function that will depend as on the length of your input. It will say how your algorithm is going to perform. So that case, it will be your prior analysis, okay, fine. The second one is your posterior testing. Posterior testing is the second task that I told you when we analyze algorithm, is that here you actually convert your program, your algorithm into your program, and then you implement your program. And when you implement your program, you check that how much time, CPU time it's utilizing, how many resources, what space it's using. Okay, so this is the actual implementation, means after your implementation, after you have implemented your algorithm. This one is before implementation. Okay, so here what you do, you choose certain parameters, and based on those parameters you devise a function that will set bounds on the efficiency of your algorithm. Fine. So if we have a look at these two, so at a very coarser level, you can see that your prior analysis, it is dependent on your algorithm, and your posterior testing, it is dependent on your program. Fine. This is the first thing. The second thing is that because algorithm is written using a pseudocode, we don't follow the syntax of any particular programming language. So this is language independent, and your posterior testing, it is language dependent. Why is it language dependent? It is language dependent because we are converting your algorithm into a program, and whenever you write a program, it will definitely be written in some language like C, or it can be in Java. So it makes it language dependent. So the third point, or the difference between these two, is that because you are not actually implementing your algorithm, you are just assuming that there's a conventional machine. So this is your hardware, or it is hardware or machine independent. Fine. Why? Because we are not implementing it actually. We are not executing it actually on a particular machine. So if you are having, say, 10 algorithms, you can easily go and you can analyze them using prior analysis. You don't need to worry about the types of machines. Why? Because we know for all those 10 machines we are having a conventional machine. But if we think of posterior testing, whenever we are going for posterior testing, we are writing a program, we are writing it in a particular language, and we are executing it on some machine. So it will be hardware or machine dependent. Fine. The last thing is that what will be the output here in your prior analysis, or what will be the things that you'll be working with? You'll be working with functions. Means you will devise some, or you will generate some mathematical functions that will set bounds, that will say that how your algorithm is going to work, okay, or perform. But in posterior testing, what do we have? We have actual bytes and numbers. We have actual numbers and byte, means you see how many bytes of memory it's taking, you have actual numbers, you see how much CPU time it's taking. Okay, so that is the major difference and the definition of these two types of analysis. One is called as the prior analysis, and the second one is called as your posterior testing. Fine. So now we will actually see a small procedure, and we'll see how can we say how much time it is taking. Fine. Based on the assumptions that we have already made, and those assumptions are that we will assume that the number of operations will actually define the cost, that is the time that your algorithm is going to take. Fine. So now we have to look at the time and space complexity. Okay, so time and space complexity are the tools that help us in the analysis of your algorithm. What do you mean by time and space complexity? In the most basic terms, we can say time complexity is the amount of time taken by your algorithm, and what is the time? That time is your CPU time, and space means your memory, means the amount of memory that is taken by your algorithm. Fine. So if we formally define time complexity is the amount of time that your algorithm takes as a function of the length of input. Okay. Now the parameter here is your length of input, and space complexity will be defined as the amount of space or memory that will be taken by your algorithm as a function of length of input again. Okay. So in both the cases we are taking the length of input. Fine. So now I will take a small procedure, and I will show you how do we calculate, calculate the time complexity of that procedure. Fine. So So I have written a small procedure here. Okay. So what we are doing is that it's a simple for loop. We are going from 1 to the length of a. A here is an array. What we are doing is that we are looking for an element x. So x is our key element that you have to find. We are simply using a for loop. We are going from 1 to the length of a, and we are checking if ai means the current element. If it is equal to x, means your key element, then we will return true. We will say that element is present, else we will return false. Now before we started this time and space complexity, I told you that we have to assume that the major cost will be incurred by the number of operations. So if we look at this statement, means this one, if ai is equal to x, how many times will this statement be executed? So this depends on the value of x. Say if your a is having elements 4, 7, 8 and 2, this is your a. So if value of x is 4, so then it will be executed only once. If your value of x is 2, it will be executed 4 times, because it has to check this condition will be executed 4 times. And if your, so what's the worst case? The worst case is that the value of x is 2, means the last element, or your element is not present. So we will assume that the length of your array a is n. So in worst case, it will take time n. But how much time it will take for each turn, means for each comparison? We have already assumed that the comparison will take a fixed amount of time. Say we will say it will take a fixed amount of time, that is c. So this statement is going to take n cross c. Why? It will be executed n times in worst case. Okay, we are assuming worst case here. And if the element is not present, this statement will be executed only once, means at the end. So this statement will be only executed once, that is c times. Fine. So if we add now these two, what's the total number of operations? That will be n cross c plus c. If you take c common, it will be n plus 1. Okay. So this is what I mean when I say that how much time this algorithm is going to take depends on the function based on the length of input. So this n is the length of array here. So we have defined the running time of this algorithm in terms of a function based on the length of input. So this is what your prior analysis means. This is what your time complexity means. Fine. We will now see some examples, and in those examples we will calculate both your time complexity as well as your space complexity, and that will clear things up. Fine. So we have an example here, an algorithm. What this algorithm does is a pretty trivial thing. It adds, the elements in your array A. So I have used the pseudocode conventions that we have already discussed. This is the algorithm name sum a comma n. So we begin in your variable sum, that is s, we put value 0. Then we use a simple for loop. We go from 0 to n, means we traverse the whole length of your array. We keep repeatedly adding the values of your AI, and we will repeat this thing until your whole array is exhausted. After that, we will return s, and that will give us the sum of your array. So now what we will do is that we will try to calculate two things. The first one is your time complexity, and the second one is your space complexity. Fine. So if we see in terms of time, what will happen is that this will execute how many times? This will execute n plus 1 times, means it will go from 0 up to n. Fine. So that will mean n plus 1. First, this statement, because when we considered the operations, there we also considered the assignment operation. So this operation is going to take a fixed unit of time, that is 1 unit of time. Okay. This operation is going to take n plus 1 units of time, because this loop will be executed n plus 1 in the last, why n plus 1? Because at the end, the state it will be false, means I will be greater than n, and then it will exit. Fine. And how many times will this be executed, this statement? How many times will be the elements added? Elements will be added n times. Fine. And finally, this return statement. It will be, because this return statement will be treated as a function call. Why? Because it will go back to the calling function, the function where this algorithm sum was called, okay? So this will again take a single unit of time. So now all we have to do is we have to add these things. So if we add these things, we will get n plus n is 2n, and 1 plus 2 plus 1 is 3. So this is 2n plus 3 is the running time complexity of your algorithm. Fine. Now we will see the space complexity. So by space complexity, we simply means the amount of memory it takes. So how many, what memory it will take? You see, S will take 1 unit of memory. We don't know how much that is. We'll just assume that it's fixed. It's 1 unit of memory. Now your A is an array. So A will take n. Why? Because its size is n. And you are having another variable I here that will also take 1 unit of memory. Fine. So we are having only 3 variables here, S, I and A. We will add these 3. We will get n plus 2. Fine. So what we can say is that if we represent a function t of n, so t will mean the time complexity of this algorithm will be equal to 2n plus 3. Fine. Here. And if we represent the space complexity of this algorithm by S of n, it will be equal to n plus 2. Now, here's an interesting thing. We are actually, in this equation, we are only interested in the higher order term. So the higher order term is here n. So we are interested in this term. Here the higher order term is n. And to be more specific, we are interested in this. We are not interested in the constant, we are interested in this. So we can say the degree here, degree is n, and here also the degree is n. So if somebody will ask you what is the space and time complexity of this algorithm, we'll say n. Why do we say n? Why are we only bothered about the higher order terms? Why are we not considering these constants associated with the leading terms? That we will understand later. But for now, you have to understand the higher order term. We are only taking that here it will be of degree n. Okay. So we will see another example. There we can again calculate the both of these things, time as well as your space. So we will take another example. This algorithm, what it does, it is multiplying 2 matrices. We are having 2-dimensional arrays A and B, and n is here the length. And what this algorithm is doing is that it is multiplying A cross B. So if we multiply 2 matrices, you know that we have to take the row of the first matrix and then multiply it with the column, and we have to repeatedly add those values. So what we do is that we need 3 for loops. So these 2 are the outer for loops. I will go from 0 to n, j will go from 0 to n, and each time what we have to do for each the third C matrix where we are multiplying these 2, we are initializing it to first to 0. Then we have to take another loop that will repeatedly add multiply the elements of your first matrix with the column of your second matrix, and it will go on adding it. Okay, so this is the logic behind the multiplication of matrix. We are not bothered about that. What we want to see here is the time complexity first of this algorithm. Fine. So if we look at the time complexity of your algorithm, again we can see that this loop will go from 0 to n. Fine. So how many times will this loop be executed? It will be executed n plus 1 times. Fine. Then if we look at this loop will be itself executed n times, but because it is inside this loop, it will be n multiplied by n plus 1, because it will itself be executed n times because it's inside the outer loop. That's why I have multiplied it. Now if we will look at this thing, how many times will this be initialized? it is equal to the number of elements in that in that array, and that will be equal to n multiplied by n. Okay, n multiplied by n. So for these many times, what will happen? That your Cij will be set to 0. The third loop, when it will come to this third loop, it will itself be executed n times, plus if you have to multiply it because it's inside this loop, so it will be multiplied by n, and then it is in turn inside this loop, it will be multiplied by n plus 1. Fine. So we can keep a multiplication sign here, that will make it, you can understand it better. And how many times will this statement be executed? It will again be executed n cross n cross n times. Fine. And then this is repeat. So it we won't take any time for this. This is repeat and this is repeat, and it will end. So now what we have to do? We have to simply add these things. So to add these things, we have to see what we have here. We are having n plus 1. Then we are having n square plus n. We have to plus n square plus n. Then here we are having again n square. Then here we are having n into n is n square, multiplied by n is n cube. Then we have to add n square into 1 is n square. Then finally we are having here again n cube. Okay. So if I add these terms up, we have n cube and n cube. We will get 2n cube. We are having here n square, and n square. It's 3 times, so we are having 3n square. And then we are having n 2 times n, so we are having 2n. And finally we are having a constant 1, that will be plus 1. So if we show the running time complexity of your algorithm, it will be equal to 2n cube plus 3n square plus 2n plus 1. Now, like I said before, the higher order term is here this, and if we if we neglect the constant associated with it, it will be n cube. So the degree will be n cube. So we can say the running time complexity of your this algorithm is n cube. Fine. So if we go for now space, how much space it will take? We are having I, j, and k. These are 3 variables: I, j, and k. They will take as one unit of memory. Then we are having C, A, and B. These are 3 arrays, and they are taking how much? Because they are all 2-dimensional arrays, so, or matrices, they are only going to take n square, and n square time, means n multiplied by n. Okay. So that's all the variables we have here. So if we add it, it will be your space complexity will be equal to n square plus n square plus n square, that is 3n square plus 1. If we go for constant, it's 1 plus 2 plus 3, so it's plus 3. So your space complexity here is 3n square plus 3, and the higher order term is n square, so we can say that it is of the order n square. So in the previous example, we saw the time and space complexities both were of the order n, but here if we see, the time complexity is of the degree n cube, or we also call it order, and you will learn it later on what order actually means. And here it is of n square. Okay, so it's not necessary that time and space complexities will be of same order. They can be of same order, or they can be of different degrees or different orders. Okay, so now we will see another example, and because in our analysis of algorithms we are mostly focusing on the time. Okay, so we are going only for the time analysis. So what we will do is that in the next examples we will only be looking at the time complexities A. B, we won't be using this pseudo code because it makes things little bit complex to understand. We'll be using simple for loops, and because almost all of you are familiar with C language, what we'll be doing, we'll be taking small for loops using C language, and we'll be quickly calculating their running time complexities, because once you do that, then only you will actually get the grasp of this concept that what time complexity actually means. Fine. So now if we look at another example, here again we have to check the time complexity. So what we'll do, we'll see how many times the different instructions are executed. So because we are counting the number of times an instruction is executed, this method is called as the frequency count method. Means we are simply counting the frequency or the number of the occurrences of your instructions. So here you can see we are having a nested loop. Okay, so you might be thinking that okay, it will be equal to n multiplied by n square. It may be equal to n square or not, doesn't matter, but you have to go through a proper procedure. If we look here, the outer loop is going from 0 to n, fine, but the inner loop is going from 0 to I. So there's a catch. You have to actually see how many times it will be executed. So if I simply draw here a small table, I see the values of I see the values of j, and I see how many times the statements will be executed. So I have written here statements in comments, means you can write any statement here, doesn't matter. So when I will be 0 means the start of this loop. So j will also be 0. So because I is not less than j, no statement will be executed, okay. So here the number of times statement executed is 0, fine. Now when I will become 1, j will initially be 0, okay. It is less than this, so number of times the statement executed is once. Then it will become 1. 1 is not less than 1, means the statement will not be executed. Then it will become 2, fine. So when it will become 2, j will go from 0, 1 to 2, fine. And what will happen here, once one statement will be executed because j is less than I. Here again, one statement will be executed. Here statements will not be executed. Why? Because I is equal to j. So total here 2 times statements will be executed. Here 1 time statement will be executed. Fine. So if we go for 3, j will go to 0, 1, 2 and 3. Here once, and here once. So total 3 times statements will be executed. So if we go on in this manner, when your I will become n times your statements will be executed. So what is the total number of times your statement is, what is the total number of statements? So you have to add these values. What we will do is that we'll simply add 1 plus 2 plus 3 plus so on to n. And what is this? This is the sum of n natural numbers. It is equal to n into n plus 1 divided by 2. So it will be n square plus n divided by 2. Okay. So this is the running time complexity of this for loop. Fine. So again here the higher order term is n square. So it is of the order, or it is of the degree n square. Fine. So this is one type of for loop that we can have. And this is how actually we analyze your algorithm. We analyze using frequency count method. We actually count the number of times that this operation is occurring. We'll take another simple for loop which looks simple, but its running time complexity is something different. It's not linear, it's not even quadratic, it's not n square or n cube. So for example, I will take an example. Look at this, this example. It looks a very simple example. So how many times do you think this statement will be executed? So you can quickly jump and say that because it's from I to n, it will be n times. But if we, check it like this, it won't be n times. Why? Because if we will go with it, initially I value will be 1, fine. And after 1, it's not stepping 1, but it's stepping, it's going twice. So after 1, it will be 2. After 2, we are multiplying again 2 by 2, that is 2 square. After that, we are again multiplying it by how much? 2 cube. So it will go on. It will go on and on until when it becomes 2 raised power k. We don't know how many times it will go and what will be the last, because we don't know what n is. Okay. So we know that I value will go from 1 up to 2 raised power k, where k can be anything. But we know that there is something that is this. This is make it stop. What will make it stop? Once your I will be greater than or equal to n, it will stop. Why? Because the condition here is I should be less than n. So when will this stop? We assume that it will go up to 2 raised power k. So that means 2 raised power k will be greater than or equal to n, because at that time I will be equal to 2 raised power k. Fine. So we will leave aside greater than sign. We'll only take the base condition, that is equal to. So it will imply that 2 raised power k will be equal to n. Fine. So if we take log on both sides, it will be log of 2 raised power k will be equal to log of n. Fine. And this is log a raised power b. This will be b log a. So this will be k times log of 2 will be equal to log of n. So log of 2 is 1. It will imply that k is equal to log n. So we get k equals log n. Means the time complexity of this algorithm is log n. It's not n. You thought that it's loop. No, loop is fine, but we have to see how many times this loop will execute. If there was a single step, means there was simply I plus plus or I plus 1, at that time the time complexity would have been n. But every time it's going twice, okay, it's getting multiplied by 2. So you have to actually count. You have to see how many times your loop will execute. You have to assume that it will go for k times, and then you have to find the value of that k in terms of your n. You get that equal to log n, and that will be the number of times your loop will be executed. Fine. So I hope that these examples made it clear to you that what time complexity is, and what frequency count method is, and how we use it to calculate the time complexities of your algorithm, which is nothing, which is simply the time required by your algorithm as a function of the length of input. So here this is a function and dependent on n. What's n? Length of input. Again here, if we see, it is t of n is n square plus n by 2. It's a function based dependent on the length of input. Okay. So this is your time complexity. So in today's lecture, we begin with the analysis of algorithm. I told you the reason why we do analysis of algorithm. Then I told you about the assumptions that we make about our machine, our conventional machine. Then I told you about the types of analysis, that is prior analysis and posterior testing. After that, I gave you the concept of time and space complexity. I gave you the definition of time and space complexity. Then we saw some algorithms, and we saw how using frequency count method we can calculate the time complexity and as well as the space complexity of your algorithm. Okay. So in the end, we saw these two examples, and we only focused on the time complexities because in our study we are only focusing on your the analysis based on your time complexities. Okay, we are not going for your space complexity. So this is all for today's lecture. I hope to see you in next lecture. Thank you.